Okay, in this problem we have a rubber band stretched out with a 4.5 kilogram mass attached to it. And the mass is initially at velocity 0, it's released, and between this point and this point the rubber band does 56 joules of work on the object. Question is, what happens to the potential energy of the system? Well, the potential energy goes down by 56 joules. The assumption is that there's no dissipation, no other forces acting, and we want to find the kinetic energy. Well, if there's no dissipation and there are no other forces acting, then all we've got is the kinetic and potential energies, and the changes in kinetic and potential energy add up to 0. So the change in kinetic will be the negative of the change in potential, will be the negative of the negative 56 joules, or 56 joules of change. So we want to find the velocity of the object here. If the initial velocity is 0, the final kinetic energy is just equal to the change in kinetic energy, which is 56 joules, so that the 1/2 m times final velocity squared is equal to the final kinetic energy. We solve for the final velocity. Just plug in the 56 joule change in kinetic energy and the 4.5 kilogram mass and do the calculation. We end up with 5 meters per second. Now here we have a slightly more complex situation. We've got an object of mass 6.5 kilograms moving at 8.6 meters per second. It's going to be stopped by a rubber band. Let's say the rubber band is stretched out between two strong posts here. So the object comes in and stretches out the rubber band, and at the instant the rubber band stops, or the object stops, we catch the object in the rubber band and hold it for a few seconds. During that time, well, you can experience this. I've got a couple of demonstrations that you've probably seen. If you stretch a rubber band out quickly and then let it snap back quickly while holding the side of the rubber band against your upper lip, just above your upper lip where it's very heat sensitive, you can feel that when a rubber band stretches, it heats up, and when it snaps back, it cools off. Don't go snapping your lips, but just hold the rubber band against your lip while you stretch it suddenly and then let it release suddenly, and you can feel that. Okay, so that as the rubber band stretches out, the frictional forces and so forth heat the thing up, and let's say that it's heated up so that it has 65 joules of thermal energy to dissipate back to the room before it reaches room temperature. Okay? And then we release and shoot the object back. Okay, what's going to happen? What's going to be the kinetic energy of the object here? What's going to be its velocity here? Well, let's look at the stuff in red. Here the kinetic energy can be easily calculated, and that comes out to be 240 joules, just 1/2 mv squared. There's your m, there's your v. So that when the rubber band is compressed here, the potential energy is initially 240 joules. However, the 65 joules dissipate, and the potential energy goes down to 175 joules. 240 minus 65 is 175. So when the object is shot back, presumably it's only going to have 175 joules of kinetic energy. Now what actually happens is a little more subtle than that. The rubber band cools, and the thermal energy lost, actually some of that thermal energy goes back into the object here. We won't analyze that completely. We won't even include that, but that really does happen. So it would be somewhat greater than 175 joules, but it wouldn't be as great as the kinetic energy that it came in with, because there is going to be some net loss of thermal energy to the atmosphere or to the surroundings. So the kinetic energy of 175 joules, and I note really more the rubber band cools, that really gives you more kinetic energy there. But if it's 175 joules, then the velocity is calculated in the usual manner as the square root of 2 ke over m, and uses 175 joules for the ke and the 6.5 kilograms for the mass. Do the calculation. You end up with 7.3 meters per second. So the object doesn't come back with quite as much velocity or energy as it had when it went in.